Chapter 7 is going to be all about polynomial functions, and lesson 7.1 is going to be a good introduction to all of that. Polynomial functions, recall that a polynomial is a monomial or a sum of monomials. The expression 3r squared minus 3r plus 1 is a polynomial in one variable because it specifically contains only one variable, that r. It only happens twice there. And remember, that would just be an expression because there is no equal sign. So a function would be, let's set that equal to another, like a function. So 3r squared minus 3r plus 1 equals function of r. So then all of a sudden that becomes a polynomial function. Now, looking back specifically just at polynomials, the degree of a polynomial in one variable is the greatest exponent of its variable. So we just find wherever we have a variable and we find the powers of that, and the highest power then is known as the degree of that polynomial. The leading coefficient of the polynomial is the coefficient of that term that has the highest degree. So I'll kind of go through and show you what that looks like, given some examples. So if the type of polynomial we're looking for is a constant, that means maybe for example we'd have 9, just straight up 9. There's no variable included here, it's just 9. Technically there's a variable, it would be x to the 0th power. This is 9x to the 0th power. Since, because x to the 0th power, anything to the 0th power is 1, 9 times 1, we're just left with 9. So technically, because the x is to the 0th power, our degree is 0. And our leading coefficient, again, that coefficient that goes along with our variable to its highest term, leading coefficient then is 9, because 9 is the one out front. Now if our polynomial is linear, remember we usually look at like y equals mx plus b. Linear would just kind of create a line. So there's going to be the one variable x, and the highest power would be 1. So for example, we'd have this x minus 2. Well, notice how x is only to the first power, x to the 1. So its degree is just 1. The leading coefficient is that term that comes out in front of it here. Well, there's nothing there, so it's kind of assumed it's 1x. So the leading coefficient is just 1. After linear, there's quadratics. Remember, quadratic is any time that we have like an x squared. So for example, we'd have 3x squared plus 4x minus 5. Again, the highest power is 2. It's to the second power. So we call it a second degree polynomial or a quadratic. And then where we see x to the 2 out front here, the coefficient in front of that is 3. So we'd say our leading coefficient is 3. We can say the same thing with cubics. Those just have a x cubed in them, like this case 4x cubed minus 6. So again, our degree is 3 because it's x to the third power. That's our highest power of x. And our leading coefficient is 4 because 4 is this one out front, the highest power. So in general, our general form is if we have all of these versions, all these different terms, so all of these a sub 0, a sub 1, a sub n minus 2, a sub n minus 1, those are all the coefficients that come in front of x, and then those are being multiplied by different powers of x, x to the n, x to the n minus 1, x to the 2, x to the a plus n, or, oh, I guess actually that would be x to the 0th plus a sub n. So at the end of this, looks like this is actually just a constant. Well, in those general forms, the degree is the nth power, because this is x to the n. And the leading coefficient was this a sub n that came out, or a sub 0 that came out front here. That's our leading coefficient. So that's kind of how those polynomials work. So if we just need to state the degree and leading coefficient of each polynomial in one variable, if it's not a polynomial in one variable, explain why. So here are just some examples here. So if we have 7x to the 4th plus 5x squared plus x minus 9, this is a polynomial in one variable. Notice it's just x, x, and x. There's no other variables, which means then the degree is the highest power we have, 4. Degree is 4. And the leading coefficient is whichever one accompanies x to the 4th, so it's 7 right there. Pretty easy. So in this case we have 8x squared plus 3xy minus 2y squared. This one is not a polynomial in one variable because it has two variables, x and y. So we don't have to continue on with that one. In this case, we have 7x to the 6th minus 4x cubed plus 1 over x. This one is technically not a polynomial. Whenever we have 1 over x, that cannot be written in the form x to the power of n, where n is a non-negative integer. Technically, 1 over x is the same as saying x to the negative 1. So you'd think, oh, that's just another power of x. But this negative 1, we can't have an x power that is negative. If it's x to a negative power, that means not a polynomial. So anytime it's x to a negative power, no longer a polynomial. So C is just not a polynomial. And for this last one, if we have 1/2 x squared plus 2x cubed minus x to the 5th power, and we want to rewrite it so that the powers of x are in descending order, or decreasing or descending. A lot of times you'll see it written as descending order. That just means that we start at our highest power and work our way down. So we would write it as negative x to the 5th plus 2x cubed plus 1/2 x squared. And it's easier to organize it if we have the highest power. So start at the top and just work our way down. 5, 3, 2. It is still a polynomial, and it is in one variable, just x. The degree is 5. That's the highest power we have. And that leading coefficient, the one that is out in front here, is technically negative 1. So that's how those ones would work. Now, a polynomial equation used to represent a function is called a polynomial function. So for example, if we have the equation f of x equals 4x squared minus 5x plus 2, that's a certain quadratic polynomial function. And the equation p of x equals 2x cubed plus 4x squared minus 5x plus 7, that's a cubic polynomial function. Other polynomial functions can be defined by the following general rule. If you know an element in the domain of any polynomial function, you can find the corresponding value in the range. So by that we just mean, let's say I had f of x equals x minus 2. So if you know an element of the domain of a polynomial function, you can find the corresponding value. So let's say we know that 2 is in the domain, so we want to find f of 2. Well, I just plug 2 in right here. 2 minus 2 would be 0, so f of 2 is 0. So let's see how that pans out in a couple more examples. If we have f of r equals 3r squared minus 3r plus 1, and we want to find f of 1, f of 2, and f of 3. Well, f of 1, again, we just plug 1 in every time we see r. So instead of 3r squared minus 3r plus 1, it's 3 times the amount, 1 squared, minus 3 times 1 plus 1. Well, 1 squared is 1, and 3 times 1 is just 3. That's where that piece comes from. Actually, I'm going to use this purple color. Right here, 3 times 1 is just 3, and we have the plus 1. 3 minus 3 cancels out, so we are just left with 1. Same thing with f of 2. Everywhere we see r, we just plug in 2. So it would be 3r squared becomes 3 times 2 squared. Well, 2 squared is 4 times 3 is 12. That's where that one came from. 3r, 3 times 2, 3 times 2 is 6. And in all these cases, we still have to add 1. So 12 minus 6, that's 6, plus 1 is 7. And one more case when we have f is, or f of r, where r is 3. So f of 3, we would say then, for every r, we just replace it with 3. 3 squared is 9, times 3 is 27. 3 times 3 is 9, right there, plus the 1 still. 27 minus 9 is 18. 18 plus 1 becomes 19. So we literally just plug in whatever value we have here and for our r values. Now, what if the value that we're trying to plug in is still another variable? So it's not as simple as just plugging in numeric values. Well, we would do the same thing as we would normally do with the numeric values, only apply that to variables. And so what I mean is, in this case, if we want to find p of a squared, if p of x is x cubed plus 4x squared minus 5x. So again, that just means everywhere that we see an x, I suppose this one should be red too, everywhere that we see an x, we plug in our a squared. So instead of x cubed plus 4x squared plus 5x, it's a squared cubed plus 4a squared squared minus 5a squared. So we would just solve out each piece individually. So a squared cubed, 2 times 3 is 6, so it would be a to the 6th power. A squared squared, 2 times 2 is 4, so this piece becomes 4a to the 4th power. And similarly, this becomes 5a squared. So we basically, like I said, just replace each piece with our variables. For this next one, if we want to find q of a plus 1 minus 2q of a. So this is the whole expression we're looking for when our q of x equals x squared plus 3x plus 4. So this is going to have a fair amount of substituting in and replacing. So when we want to evaluate the q of a plus 1 part, that just means every x that we see we replace with a plus 1. So instead of x squared plus 3x plus 4, it's a plus 1 squared plus 3 times a plus 1 plus 4. A plus 1 squared becomes a squared plus 2a plus 1. 3 times a plus 1 becomes 3a plus 3, and still add 4. Then combining all of our like terms, we get a squared plus 5a plus 8. So that was one part of it. Now to evaluate the 2qa, we replace x with a in every piece, then multiply the whole thing by 2. So everywhere we see x, we put in a, and then we multiply everything by 2. So 2 times a squared plus 3a plus 4. So 2a squared plus 6a plus 8. Now, at the end of all that, we want to take this piece here that we had underlined in red, and we want to subtract the piece here that we underlined in green. Because again, that would be this piece minus this piece. So it would look like a squared plus 5a plus 8, that was our red underline, minus 2a squared plus 6a plus 8, that was our green underline. Now we just distribute that negative to each piece individually. So a squared plus 5a plus 8 minus 2a squared minus 6a minus 8. And combine all of our like terms. We are left with, in the end, negative a squared minus a.